Congratulations! You just got some AI contract work with an e-commerce company based in New York City that sells clothing online, but they also have in-store style and clothing advice sessions. Customers come into the store, have sessions or meetings with a personal stylist, then they can go home and order either on a mobile app or website for the clothes they want. The owner spotted the AI bug recently, so they hired you to build an AI model to predict how much their customers would be spending annually. The company works on a membership basis and maintains a dataset of all their customers. They are also trying to decide whether to focus their efforts on their mobile app experience or their website. They want you to help them figure it out. So let's get started. Here, we will follow the steps below to analyze the customer data which company provided. It's a made up data for this project, and then try to build a model to predict customers' annual spend. So feel free to work alongside if you want to practice these codes too. The dataset has been linked in the description box in case you want to code along to practice your Python skills. You can download this dataset and move it in the same folder as the Jupyter notebook that you would be using. Otherwise, feel free to just watch along. Let's start by importing some of our regular libraries. So here we imported NumPy, pandas, matplotlib.pyplot, splt, seaborn, and we also ran the one line code %matplotlib inline, which is used for showing the visualizations in the Jupyter notebook. Next, we need to get the data. Today we will work with an e-commerce customer CSV file which we received from the company. So let's read in this data and see what it has. We will name it customers as our variable for the data frame. Use pd.read underscore CSV, and as you begin typing, press tab. It will show you all of the options in the folder. You have your Jupyter notebook. Select your CSV file and press enter. Now let's check what this data frame has. Let's check the head first. So here, as you can see, and the company has provided us this information as well. It has some customer information such as email address and their color avatars. After that, we have average session length, which is the average session of in-store style advice sessions. This is in minutes. Then we have time on app and time on website. Those are in minutes as well. And then we have length of membership, that is in years. And then we have yearly amount spent, which is in dollars. So let's check the info of this data frame to see how much data is there. So in total there are 500 entries ranging row index ranging from 0 to 499. There are total 8 columns as we have seen above. First 3 are an object data type, which is basically just the string data type, and the next 5 are float as we have seen already here. The first 3, average session length, time on app and time on website, are in minutes. Length of membership is in years, and the yearly amount spent is in dollars. Next, let's do some analysis on this data frame. We will use the describe method, and what it will do is for each of the numerical columns it will accumulate some stats and throw it up here. So as you can see, the total data for each of this column is 500 rows. It will give us the mean, the standard deviation, minimum value, maximum value, and the 25 percentile, 50 percentile, and 75 percentile data for each of the columns. Let's analyze this a bit. The first average session length, the minimum value is 29.5 minutes, the maximum is 36, and you can see the 25th first quartile. This is called first quartile, second quartile, and third quartile. So that is 32 minutes, 33 minutes, 33 minutes. Average is 33 minutes, and standard deviation is just under 1 minute. So what this means is uh, standard dev sigma is called the distance of standard deviation from the mean. So 2 sigma would be plus minus around that mean. So 1 minute minus and 1 minute plus, that would be from 32 to 34 minutes. So what does 1 sigma or 2 sigma means is 66% of the total data is within that distance. 96% of the data is within 4 sigma, that is minus 2 sigma and plus 2 sigma, and 99% of the data is within uh, 6 sigma, that is minus 3 standard deviation to plus 3 standard deviation. So if you do that here, you can take the time from 30 minutes to 36 minutes, and 99% of that data would be within that interval. Now that you understand that, let's analyze the other columns as well. The time on app varies from 8.5 minimum to 15 minutes maximum, with different quartiles been 11 and 12 minutes. Average was 12 minutes, and standard deviation once again was just under a minute. So that basically means 99% of the data is from 9 to 15 minutes. 66% of the data is from 11 to 13 minutes, roughly speaking. As for the time on website, the minimum was 33.9 minutes, maximum was 40 minutes. So it's really higher than time spent on app. If you see here, it's almost 3 times. The time spent on website is almost 3 times the time spent on app. The standard deviation is again just 1 minute. Mean is 37. So 66% of the data varies between 36 to 38 minutes. As for the length of membership, the minimum given here is 0.26, but if somebody becomes a member today, it would be 0, right? So minimum is 0. The maximum is 6.9 years. So the oldest customer is about 7 years old. And the average for all of their data is 3.5, with again standard deviation is just 1 year. Length of membership is in years, so 66% of their customers have been member between 2.5 years to 4.5 years. And then for yearly amount spent, the minimum amount somebody spent last year was $256, maximum was $765, and you can see other quartiles here. Average was $500 and standard deviation was $80. So again, 66% of the data was between $420, roughly speaking, to about $580. That is where an average customer is. Now let's move on. Let's do some exploratory data analysis. So for the rest of this exercise, we will only be using the numerical data. We won't be working with any of the object columns or string columns for now for this exercise. So first up, we have to create a joint plot to compare the time on website and yearly amount spent columns. Does the correlation make sense? So let's take a look at our data frame. We have to plot between this column time on website and yearly spent amount. So here we'll do sns.jointplot. So here we need to put in 3 things. One is our data frame, then x and y variables. Data is customer's data frame. For x, we will give the column time on website. For y, we will select yearly amount spent. Let's run this. So does the correlation make sense? So here we see as the time spent on website, which is on the x-axis, increases, there is no pattern to say the yearly amount spent increases. Even during this range of 35 to 36 minutes, you can see there are spent in the range of $400, there are spent in the range of $600 to $700 as well. As you go higher from 36 to $37, uh, the spend varies from $400 to $600 $700, and the same happens at 38 39 minutes as well. So there is really no correlation here. That means the time spent on website does not have any impact or any correlation with the amount people spend by making their purchase decisions. Now let's do the same thing with time on app. So here we do see a pattern, even though it's not a very strong pattern. But as the time on app goes higher from 9, 10, 11 minutes to 13, 14, and 15 minutes, there is a general pattern of yearly amount spent being higher. Those who spend less amount of time on the app, they spend around 300, 400, $500, and those who spend 14, 15 minutes on the app in general are spending about $600 to $700. So there is some correlation between the time spent on app and the yearly amount spent. So next, we have to create a 2D hex bin plot comparing time on app and length of membership. So here, the way to do that is if you select kind parameter, check the signature of this joint plot. The kind parameter by default is given as scatter, but if you go down and check this parameter, we have options here for scatter, KDE, haste plot, hex plot, reg plot, and reset. These are different kinds of plot. What we need here is a hex bin plot. So we'll select hex, run this, and now what we have is a 2D hex bin plot. The darker plots have more data points inside the hexagonal area, and lighter plots have less data points inside that hexagon. So here, as you see, as the time on time spent on app goes up, there is really no pattern here. There's no correlation between the time spent on app and length of membership. Both of these, as you can see by histogram here, both the time spent on app and length of membership is fairly normally distributed about their mean. So now let's explore these type of relationships across the entire data set using a pair plot. So rather than checking for all numerical pairs manually, we can just plot this using pair plot. We just need to give in this data frame name, and this can sometimes take a while to run. So we don't see any general pattern for anything here. All the diagonal elements are just histogram for univariate data, that is average session length. Just for that column, it shows the distribution of the data, which is fairly uh, uniformly distributed. Similarly, for time spent on app, time spent on website, length of membership, and yearly amount spent. So if we focus on this column, yearly amount spent, this is compared to all other numerical columns. You see, for this length of membership, there is a general pattern here. As the length of membership goes up, the yearly amount spent goes up as well. You won't see any spend around $400 for the length of when the length of membership is 6 years. It's much higher, around $600 to $700. Similarly, for new members which are within 2 years, they don't spend high amount like $600 to $700. So this is a clear correlation here. So there is a clear correlation here. As the length of membership goes up, yearly amount spent goes up as well. Compare this to other metrics we have, such as average session length, time on app, and time on website. These really don't have any patterns, though you can say time on app has some pattern, not as strong a correlation as the length of membership, but there is a general pattern where if people spend more, those who spend more times on app tend to spend higher amount. There is some correlation, but a moderate one. But if you compare that to time spent on website, there's really no correlation at all. Based off this plot, what looks to be the most correlated feature with yearly amount spent? Clearly length of membership. Of membership is clearly most correlated with the yearly amount spent. Let's check the correlation for all of these uh, data. We'll just use the CORR method. So it shows an error, and that would be because of the string values. So what we can do here is, if you check the signature, there is an option for numeric only, which is given as false by default. So pass in true for that, and now it gives the correlation for all of the numeric columns. So we will focus on the yearly amount spent, and we have the correlation with all of the other columns here. If you compare it with average session length, time on app, time on website, and length of membership, clearly the length of membership has more strong correlation. Now remember, the correlation varies between -1 and 1, with 1 being the strongest correlation and -1 being the strongest correlation on the negative side. That is, if one variable goes up, the other variable will go down. Correlation shows the linear relationship between two variables. So here, clearly the length of membership is showing a correlation of zero point 0.8 with yearly amount spent, which is fairly strong correlation. The time spent on app shows a fairly moderate correlation with yearly amount spent, but the time spent on website has almost no correlation. This is very close to zero. This is practically zero. Average session length once again has a very mild correlation. We won't give much weightage to this. Now next, let's create a linear model plot of yearly amount spent versus length of membership. So for this, we will use lmplot. Data is customers. X is length of membership. Y is equal to yearly amount spent. We got an error, length of the spelling of length is wrong. This happens. So clearly there is a relationship between the two, and we have a good fit here as well. So next what we will do is, we have explored our data a bit. We will begin building a model for this now. Let's go ahead and split the data into our training and testing sets. Set a variable x is equal to numerical features of the column and variable y equal to the yearly amount spent column. So here we will begin building our model now. We will split our data into training and testing sets so that once we have built a model, we can test that model on the testing data set. Now here we have to create two variables. One is x, and remember this x is capital X, which will be equal to the numerical columns of the customer's data frame. This will be all independent variables, and this will namely be average session length, time on app, time on website, and length of membership. And then our dependent variable y would be small y, which will be equal to yearly amount spent. Now you may ask, why is the x capital X and not small? Well, that is by convention. uh, y would be just a single column, so it is vector, and vector is always conventionally denoted by a small letter, while x would contain many columns, actually four different columns, so it would be an array, and arrays are conventionally denoted by capital letters. So here first check our columns for this customer's data set. We will ignore this string columns and we'll focus on just this numerical columns. This yearly amount spent will be our independent, or rather the dependent data set. And for our independent data sets, we will take these customers and we'll pass in the list with these column names. Now let's quickly check our data here. So this X is 500 by 4 data frame with this session length, time on app, time on website, and length of membership as its columns. And y would be just yearly amount spent. It's a series because it has just one column. Length is 500, so this is perfect. So now that we have defined our x and y variables, we have to split the data into training and testing sets. So first, from scikitlearn, remember to install scikit package in your anaconda prompt or command prompt using either conda install scikit-learn or pip install scikit-learn before importing scikit-learn libraries in the notebook. Model selection family, we have to import the model, trend test split, run this, and now check the signature for this trend test split. This is a shortcut, just drag down, you will get this example here. Just copy paste this, don't run it for now. Now this is a shortcut. See, what we are doing here is, we have our x variable which has 4 columns and y variable which is dependent variable with only one column. So we are dividing that data into our training and testing sets. This is basically tuple unpacking. What we are doing here is, we are uh, calling this trend test split model, and we are, these are basically variables assignment. So we are passing it x underscore train, x underscore test, similarly y underscore train and y underscore test. So it will create four data sets. It will divide x into two parts, x train, x test, and then it will divide y into two parts, y train and y test. So we have our x and y variables. It will take the data from here, and then we will give a test size of 0.3, which means 30% of the data would be converted into test and 70% would be converted into training data, and we'll pass in a random state of 101. Now if you are practicing this along with me, then if you pass this random state 101, you will get the same numbers as me. Otherwise, if you don't, you may get different data and the numbers won't match. So let's run this and let's check what this x train and testing data set is. So what this did is, remember there were total 500 rows. It is dividing it into the ratio of 70% with 30%. So training data set would be 350 rows and testing data set would be 150 rows. And see, these rows are selected individually. It's not the first 70% then the next 30%. It has randomly selected 30% of the rows to be the test data, and if you would have used this random state 101, you will get the same rows selected as training data as I did, and similar rows selected as testing data, which I did. Let's check this test. This is 150 by 4 again for y data. Now that we have split our data into training and testing sets, we will train the model using this training data set. For that, we will import linear regression function from the linear model family. From scikitlearn. Now, before doing this, remember for using this scikitlearn, you will have to install scikitlearn package. You can do that at your command prompt or anaconda prompt by using conda install scikit-learn or pip install scikit-learn. Now, after you have done that, you can use this sklearn libraries. So here to instantiate a linear regression model, what we will do is from sklearn dot linear underscore model family, press tab, it will autocomplete, import linear regression. As you begin typing, press tab, it will autocomplete. Run this. Now we will instantiate an object for linear regression. Run this as a function, and if you want to see what this is right now, just run this and it's a linear regression function. It is not fitted right now because we haven't done anything. Now next we have to train this lm object on the training data set. That is simple. Just use lm.fit method, and here if you check the signature, we need to pass our x and y data. See again, x is in capital, y is in small. So x is equal to our training data set, which is x underscore train. Remember we set the variable capital X, then we divided those within x underscore test and x underscore training data. So we'll take our training data. Similarly for y, it will be y underscore train data, and run this. Now we have fitted our linear regression model. Next we will print out the intercept and coefficients, and then I will explain this equation. For that, what you can do is lm dot, if you press tab you will get many options here. You can go through these methods. For coefficient, we will use this coef underscore. For intercept, we have this option intercept and then hyphen. So run this, we'll get our intercept here. And then for coefficient, use this coefficient underscore, and we get an array for coefficients. Now what is this? But before that, let us convert this into a data frame. We'll call this CDF coefficient data frame, pd.dataframe, and for data we will use coefficient dot coef underscore. And what we need now is to pass in an index. For that, for the index we will use x dot columns. What this will give, what is x dot columns? Let's check here. If you run this, you remember x is our data frame with these four columns: average session length, time on app, time on website, and length of membership. So these will become our index here. And for columns, we can pass in a list. It will be just one uh, column, so we just need one name. We will name it coefficient. Now let's check the CDF. So we have coefficient for all four of these columns now. Now what is this linear regression equation? From your school you must remember something like y is equal to a plus bx, a linear equation like that. So that is basically a linear regression equation for one independent variable. Here the y is independent variable. If you remember that xy graph, y is the independent or rather y is the dependent variable, and all of the x0, x1, x2, x3 are dependent variables. We have multiple dependent variables here rather than just one x. And b0, b1, b2, b3 and so on are their respective coefficients, and c is a constant here. So let's suppose if the coefficients for all of these other factors x0, x1, x2, x3 are 0, this entire thing will be 0 and y will be equal to this constant in that case. And that is what this intercept is, that when x is 0, what would be the value of the y. So in this case it would be negative. So basically if the average session length is 0, time spent on app and website is 0, length of membership is 0, then the yearly amount spent would be negative, which doesn't really make any sense. In some of the equations it will have a context, it will have some meaning. In other equations it doesn't really make sense, because if you are not a member, you don't spend any time going through their app or website, you are not going to give them any money for free, right? But when these coefficients have some value, then all of the sum of that would be decreased by this amount to reach an appropriate y value. So this C is lm dot intercept, and this b0, b1, b2, b3 is this array. The first one is for x0, 0, 1, 2, 3 are our range index. This 0, 1, 2, 3 are our range index. First one is average session length, next is time on app, then it's time on website, then length of membership. That's how our x dataset was, right? Let's take a look. So we have our x dataset here, and this coefficients is an array for these four columns. So 25 is coefficient of this first column, 38 is coefficient of this second column, time on app, this is coefficient for this time on website, and this 61 is coefficient for this length of membership, and that's what we have shown here in this small data frame, so it's easier to read. So once again, basically the equation for the yearly amount spent would be this value plus b0 into x0, that is 25 into average session of length, plus b1 x1, that is 38 into time on app, plus b2 x2, that is 0.19 into time on website, and b3 x3, that is 61 into length of membership. So that is our AI model. So this is our linear regression equation, which is used to predict the yearly amount spent based on this four dependent variables. So we have our model now. Now next, let's move on to predicting testing data. So remember, we divided our data into training data and testing data, because once we have the model, we also want to test if it is performing well on new data. So now that we have fit our model, let's evaluate its performance by predicting of the test values. So here what we have to do is this lm dot we have, if you go down, we have a predict method. Just pass in here, if you check the signature, we just need to pass in one parameter, which is x, which is our testing data. So we will use this x underscore test, and we will store this as a variable called predictions. If you want to check what this will be, run this and it will return an array of about 150 data, because we had 150 data in our x testing data set. Now manually it's not possible to go through each of these. What we will do is we will compare this predicted data set with our y testing data set. So the simple way to do this is to visualize it. We can create a scatter plot of the real test values versus the predicted values. On x-axis, we will use our y underscore test data, and on y we will use our predictions data. This is a good fit. We will arrange it aesthetically. What I'm going to do is to give an outline to all of these scatter dots. Use edge color parameter, and I will pass in black, and I will try to reduce the width of this lines as well. Let's make it 0.5. This is good now, and I will also give x level and y level here. These are true values, and these are predicted values. So we have the actual values on the x-axis and predicted values on the y-axis, and for a very good fit, for 100% accurate fit, you will get a straight line uh, like this. This is a very good fit here, because all of the data points are around that point. It's very hard to get 100% accurate prediction, but so that's why this has a little bit of jitter here, but this is actually a very good fit. We will now evaluate our model. So what we will do for that is we'll check for a couple of statistical measures like root mean square error and coefficient of determination. Now don't worry too much about this. We will not go into the mathematics behind these and many other statistical measures that we have for regression models. Just know that the lower the value of these measures, the better fit our model has. However, there is no right or wrong or too high or too low answer here. everything really depends on the context and domain knowledge to know how much precision is required by the model. For example, the medical testing field would require higher accuracy and precision than the clothing store. If you want to know more about these and other statistical measures we have for regression analysis, you can search for these terms on Google and Wikipedia to know more about these. But here I will just quickly explain these two: root mean square error and coefficient of determination. This root mean square error is the square root of the mean of the squared errors. So what we have here is y and y cap. For each data point, we have y and y cap. Y is the actual value and y cap is our predicted value. Now imagine an xy plane where x is the independent variables and y is the dependent variable. So here we have two value of y. One is the predicted value and one is y is the actual value and y cap is the predicted value. So we will subtract predicted value from the actual value. It could be both positive and negative depending upon whether the predicted values was higher or lower than the actual value. So we will take a square of that distance, sum all of those up and find an average of that, and then took a square root because we squared that number. This is root mean squared error. Basically it is calculating the average of all the errors in the prediction. In the most simplest term, it is calculating the average of the errors in the prediction. What it is doing here is it is squaring those errors, then finding an average of all the squares and then using the square root over that. Now r square varies between 0 and 1. This shows how much of the variation in the dependent variable is explained by the independent variable used in the equation. So let's say if we get this number as 0.5, that would mean the 50% of the variation in the independent, or rather in the dependent variable, is explained by the independent variables we have used in this equation. So there are other variables which we do not have in this data set, but the independent variables which we have in the data set is responsible only for the 50% of the variation in the dependent variable. So higher this value, better is our figure. Now let's calculate this. What we will do is, for that we will need to import metrics from scikitlearn. Import. So we have imported our metrics library here. Run that. Check for the methods available. Start typing m. We will take this mean underscore squared error, and if you check the signature, we need to pass in two variables to find the that is the true y and predicted y. True y was y underscore test and predicted was predictions. Now we need the square root for this, so we'll run sq dot square root. This is a numpy function, and we will also print this. So what we'll do here is, let me just print rmse space and then this. We'll also print r square matrix dot. If you go down and check for r square, you have r2 underscore score, and we need to once again pass our y test data and predictions data. So within, for these two variables, it will find what was the r2 score for that. Let's print this. So let's check the R2 first. I said that the value will vary between 0 and 1, and what we have got here is 0.98, which is basically 0.99 by rounding it to 2 decimals. Now this shows that we have a very good fit here, because almost 99% variation in the uh, dependent variable is explained by the independent variables which we have here. This is a very good model. Now as far as root mean square error is concerned, we have got 8.9. This is an absolute value. 8.9 just in itself, it doesn't say us anything. What you have to do is to compare this against our predicted y values. Now remember, our y values were in the range of 300 to 700, $800, and we are getting an average error of $9. So broadly speaking, let's say a predicted value was $600, and we know the average error is $9. So the value could be anywhere from $591 to $609. This is an average error, so it could be higher or lower as well. But it doesn't really matter. If you're predicting something to be $600 and it's between 590 to 610, that is a good prediction. So we have got low value. The best way to check this is to divide by the average of all the predictions, all the predicted value, and that ratio would be a low value. These are just statistical measures to check how good a fit we have got for our model, and that is really good. We will also check for the residuals here. So we have got a good model with a good fit. Let's quickly explore the residuals, which is actual value minus predicted values, to make sure everything was okay with our data. What we are really looking here is to get a normally distributed data. For normally distributed residuals, we can use histogram for that, and we are looking to plot this between y underscore test minus predictions. So subtract all the predicted value from the actual values, run this. Let's plot more bins, because we did had 500 data set. We had 150 data set in the testing data, and I will also add in the KDE plot. Now this does looks like somewhat to be fairly normally distributed, so it's a good model, good fit. So now we have got our model and we have checked for errors. So now next, move on to the conclusion part. We still want to figure out the answer to the original question. Do we focus our effort on mobile app or website development? Or maybe that doesn't even really matter, and membership time is what is really important. Let's see if we can interpret the coefficients at all to get an idea. So first we will recall our coefficient data frame. How do we interpret this? So I've already written the answer here for you. You remember the equation: y is equal to c plus b0x0 plus b1x1 plus b2x2 plus b3x3 and so on. x1, x2, x3, x4 are these independent variables, that is average session length, time on app, time on website, and length of membership. So the way to interpret these coefficients is, if all else remain constant, that is the value of x and coefficients remain constant here, 1 unit increase in average session length is associated with an increase of $25.98 in the yearly amount spent. That is, if the amount spent on if the time spent on app and website and length of membership remains constant, we can predict that 1 unit increase in average session length will increase the yearly amount by $25.98. Now remember, this is associated with, not results in. Correlation is not causation. Just the increase in average session length will not cause an increase in yearly amount spent. It is a correlation. What we have observed is those who spend more amount of time in their session in the store, they spend more money on the app as well. Now, correlation is not causation. Increase in average session length will not directly result in increase in more dollars spent, but it is correlated. That is, those people who are spending more time in their sessions are spending more dollars as well. Similarly, for other coefficients as well, if all else remain constant, one unit increase in these independent variables will cause these much increase in the dependent variable. That is, for time in on app, 1 unit increase, that is 1 minute more spent, will result in $38. Sorry, not result, it is associated with an increase of 38 more dollars on the yearly amount spent. Time on website is just 19 cents, and length of membership, 1 unit here is 1 year, that is associated with an increase of $61.27 on the amount spent. So length of membership has the most impact on the yearly amount spent. So maintaining good customer service and retaining customers is the key to increase the revenue. Do you think the company should focus more on their mobile app or on their website? Now this is really tricky. There are really two ways to think about this. One is develop the website to catch up with the performance of the app. App has a mild correlation with the mm, amount being spent. Website doesn't have any correlation, so maybe you want to look into that. You want to develop your website so that it performs better. Or the other way to look into it is develop the app more, focus more on the app, as that is what is working right now. But this sort of answer really depends on other factors going on at the company, really, and we would probably need more data to figure this out. But one thing is for certain, that customers are spending nearly 3 times as much time on the website, as we have seen at the start of this exercise, than compared to on the app. So don't ditch it. You never know what is working, what is not. So that was it for today. Congrats on your contract job. The owners loved the insights and promised to give you a recommendation for this. So until next time, see ya.